somebody mentioned the turkey story from Black Swan. So imagine you're a newborn turkey and you're trying to make sense of the world. And every day, these creatures, which you'll call humans, give you food and drink. And after a while, you start to realize, I understand the universe. The purpose of the universe is to have these creatures give me food and drink and keep me comfortable. What eventually happens to the turkey? In high probability. Yes. It gets killed around Thanksgiving time. And this is called a black swan event, where most events are very similar, and then all of a sudden, it can be one day with wildly different behavior. When the stock market crash happened in the Great Recession, a lot of the mathematical models were very good for most days. But on days with massive movement and non-standard conditions, a lot of models completely failed. And so you can be right most of the time, but if you're wrong on the big swing days, it could be disastrous. And so what I wanted to do today was I wanted to talk a little bit about mathematical modeling. And so I'm going to do this with one of my favorite examples, baseball. Are there any Yankee fans here? Good. There's no strong hands going up. Excellent. I don't have to work on individualized exams. That's good to know. So this is joint work that I have done with some of my students over the years. We've actually published in sabermetrics journals. If you've read Moneyball, I've actually been fortunate enough to meet many of the people from that. And so what I want to do is talk a little bit about how do you do mathematical modeling. So I always dedicate this talk to my great uncle Newt. He is responsible for my son's middle name, and his wife is responsible for my daughter's first name. He assured me when I was a little kid that I would live long enough to see the Red Sox win the World Series, which when I was growing up was not a given by any stretch of the imagination.
More than 40 participants in the meeting. This meeting is being recorded. You have been put on hold by the host. You cannot listen or talk until the host releases the hold.
Okay. So in the old days, you could actually go to the ballpark with your kids. And so hopefully we will have such days again in the future. All right. So in general thought, doing research. A lot of what I'm doing becomes senior thesis at Williams, or it's become I presented at conferences. It's not that hard to get involved. Mathematics, right now, is already good enough to make significant contributions. So a lot of it, some general advice is build on what you know or what you can learn quickly. Try to figure out what's going to be interesting. What might excite you may not excite someone else. One way to excite people is how? What could you do that would make people be interested in what you're doing? How could you sell it to them? It's related to something they need. Hey, I can help your team win more games. I'm interested. I can help you win the election. I'm interested. I can help you reopen safely during COVID. I'm interested. So if you can appeal to someone, that's great. Next question is, how are you going to work? Are you going to work alone? Are you going to form groups? It's nice to have other people to work with. It makes it more fun, and you can have complementary skill sets. If you're really good at X, you don't necessarily need someone else who's good at X. You should have somebody in your group who is really good at scraping data and culling data from the internet. There is so much data now, it's incredible. When I was a postdoc at The Ohio State University, I participated in a data analysis seminar. And this was 15 plus years ago, and one of the comments stuck with me to this very day. And they said, we have satellites over the Earth that are beaming down information to predict the weather, and every day more information comes down than is in the entire Library of Congress. And we have on the order of a few hours to analyze it and make predictions. You have so much information available, and this was 15 years ago. It's even more now. When you have this much information, it's trying to figure out which things are the most important. This is a class on COVID. You can always look at this in terms of trying to model COVID. What things do we really need to really worry about? One of the things we found is that age is a terrific indicator of the severity of COVID when you get it. And this was something that was not immediately clear when it struck. It is not hitting young kids as much as some other diseases. All right, and then the big questions are, What are the questions? Well, there are various places you can go. See what other people in the field are looking at, are studying. There are baseball journals. Try to get a sense of what are the key questions. All right. So asking important questions is one of the most challenging things to do. I often like to say most of my life, I'm a trained monkey. That with the training I have, with the math skills I have, if the problem can be set up correctly, I can solve it as well as numerous of my colleagues, as well as numerous of my students. The challenge is finding the question to look at, or to find the right way to look at it so that the methods you know are going to be applicable. So look for connections between various areas. Try to be a jack of all trades. One of my favorite quotes is, if all you have is a hammer, pretty soon every problem looks like a nail. What are you good at? If you're good at hammering, can you somehow convert the problem you're given to a nail? Or even better, go to the land of the screwdriver. There's smart people there. If they could have solved it using a screwdriver, using the methods they know, they would have. I've published papers in accounting, economics, computer science, geophysics, physics, statistics, sabermetrics, marketing. The list goes on and on and on, because I can convert what they're studying to a mathematical system and apply the tools and techniques I have. And one of the goals for today's lecture is to show you, using baseball as an example, that a lot of you already have enough knowledge in basic probability and basic statistics to make a meaningful contribution. All right, and so I just mentioned the law of the hammer, writing things up. Okay, so out of curiosity, how many of you have heard of the Pythagorean, either one-loss theorem, because I'm a mathematician, or the Pythagorean one-loss formula? Okay, so I see one hand up. I'll put my hand up so we'll make it two. All right, so I actually first heard about this when I was a postdoc at Brown teaching mathematical statistics. And one of my students mentioned this to me. And so it shouldn't be too hard to figure out which one is Pythagoras and which one is Bill James, the father of sabermetrics, basically applying statistical thinking in a really good way to baseball. One of the things that really makes him influential is not just that he has good ideas and has a good sense of what to write about, but he writes well. And this is one of the reasons I'm always happy when I have a double major math English. In fact, one of my students who worked with me on problems like this years ago was a double major math English. You need to make it compelling. If you're writing about baseball, a lot of people just happen to like baseball. And so you have a nice advantage there that you might not have when you're writing about, I don't know, elliptic curves. It's more of an acquired taste in that setting. And so what Bill James did is he, for years, was like a one-man call in the dark that people were focusing on the wrong statistics. And if you read Moneyball, Moneyball is about this revolution, about trying to find what are the right statistics to look at. And to some extent, this is now beginning to fit very nicely with this course. It's a general way of looking at things. Just because everybody is showing you something doesn't mean that's what you want to see. Almost think of a magician, where their job is to misdirect you. So two of my friends actually withdrew from college for a year to help amazing James Randi set up his Magic Institute to debunk psychic claims. And just the way they can make you look at the wrong thing is absolutely amazing as to how easy it is for them to do. It's not a challenge. And I want you to have that as you're looking, because there's opportunities. When you're looking at the wrong thing, when you're focusing on the wrong thing, it's like, well, all we have to do is, this is far more important than that. If we focus on this, we're going to do much better without too much work. One of the big things is, should sick old people be sent back to long-term care facilities? And when we were starting to see the damage that was doing, it's a very easy change to make and implement. All right, so the goal of the talk is I want to give a derivation of the Pythagorean one-loss formula. It's a way to predict a team's winning percentage from very little information about the team. Essentially just how many runs they score and allow on average. I want to talk about the ideas and the techniques of modeling. And this will be applicable for those of you who are trying to do some modeling for COVID. We'll see how advanced theory enters in even simple problems. For those of you who have done calculus, do you remember the drowning swimmer problem? So you have a swimmer who is struggling in the water and the lifeguard has to get to them. What path do you think most human lifeguards take? Straight line. But if the lifeguard actually knows calculus and the beach is empty, they should think of Snell's law and angle of the refractive index and take the path that minimizes time. It is almost a straight line. It is much better to just take the straight line than for the lifeguard to take out a piece of paper and start doing the calculus. But if you look at the best path, you actually have to solve a quartic polynomial to find the best place for the lifeguard to run to. And so in a very simple problem, already good math is emerging. The same thing happens here. Huge is that there are opportunities from inefficiency. So if somebody is focusing on the wrong thing, you have a tremendous opportunity to do better. A lot of people are terrified, oh, I can't do anything valuable. I don't know how to solve the problem. You don't have to solve it. You have to do better than what other people are doing. So for those of you who are in the metrics group, you don't have to come up with the best metric for color coding counties and towns in Massachusetts. You just have to do better than the state is doing now. That is a much lower bar. And then the last is, if there's time, I'll talk a little bit about avenues for research for anybody who might be interested. Okay, so the goal is to find good statistics to describe the real world. Have I shown this slide yet in this class? Okay, so this is one of the bridges in the Boston-Cambridge area. It's about 620.1 meters in the standard way of counting. It's also 364.1 smoot plus or minus an ear. So Smoot was an undergraduate at MIT who was pledging a fraternity. And your fraternities are known for trying to find, how to phrase this, good uses of their pledge's time. And so they decided, I wonder how many times it would take us to pick up Smoot and move him all the way down the bridge. Turns out the answer is 364.1 plus or minus an ear. I love the plus or minus an ear. And so Cambridge, Boston wasn't really thrilled with all the marks on the bridge, so they had the marks removed. Fraternity was not happy because this took a lot of work. So what do you think the fraternity did? They did it again. And eventually Cambridge said to hell with it and they left the Smoot marks. Now it's been immortalized. They actually have beautiful Smoot markers on the bridge. And when there's traffic accidents, they report how many Smoots was the accident from the edge of the bridge. Is the Smoot a good unit of measurement? It's a terrible unit of measurement. It's going to be hard for somebody to reproduce what is a Smoot. A Smoot might actually be a function of time as he gets older. This is not the kind of statistic we want. We will come back and see examples of this later in the lecture. Does anybody know what happened to Smoot? So we'll talk a little bit later about what happens with Smoot. So this is the cute version of the talk. This is the first time I coached my daughter. What do you think of the picture? What do you think about the shirts that the adults are wearing? Why do you think we're wearing those shirts? Any thoughts as to why we're wearing those colored shirts?
To match the kids.
Same color as the kids. I was able to put on one of the kids' shirts. This is when they were doing T-ball. It took a while to take the shirt off. One of the adult shirts is actually blue, and the image has been digitally modified. And so the reason I'm showing this is just to show you just how easy it is to forge and fake things. And when you look at it quickly, can you even tell which adult shirt you think was modified? All right, so the goal is to go from playing T-ball level, going a little bit higher to rookie level, starting to play like travel teams and championships, to getting World Series championship rings. So this is a Red Sox World Series championship ring. I was fortunate enough to get to wear it for a few hours. I will not mention, because this is being recorded, what I offered in exchange to keep that ring. I do still have my son Cameron though. This is us at 2 o'clock collecting a foul ball that we got to hold for about a minute. It hit somebody behind us. And so, why am I showing a picture of collecting a foul ball? I want you to think about ballparks. Are all ballparks equally likely to collect a foul ball? Okay, why not?
They all have different layouts.
They all have different layouts. And your Fenway Park has almost no foul territory for fielders to run in the outfield. And so it's going to be very easy for a ball to get into the stands. So when you're trying to figure out how valuable is somebody, how valuable where, your value is going to be dependent on where you play. If you're a hitter, if you have a ballpark with very little foul territory, you're more likely to get a second chance to hit. Or if you have various layouts of the field, and so they have what's called ballpark adjustments. And for those of you who are doing the metrics, we've actually talked about trying to adjust for the fact that maybe different towns have different population densities. They might have different geographic sizes. And so maybe that should come into play when we are trying to figure out how concerned should we be that there are 5 cases in 14 days. So there's a lot we can learn from how baseball tries to adjust this. So I just lent somebody in the class a wonderful book, Baseball's All-Time Best Hitters, where they try to take into account differences in terms of the area you're playing in, the parks you're playing in. You're taking all of these into account. Anybody know a baseball era where you might have to look at the statistics, the batting statistics, with a little skepticism? Yes? The dead ball era. So there were years when Babe Ruth had more home runs than every team in Major League Baseball but one. Which team did he not have more home runs than? His own, right? Physically impossible to have more home runs than your own team. Unless maybe if you're traded in the middle of the year. So it's very hard to compare players across different eras. And so baseball has developed a lot of tools so we can say, well, what would happen if Babe Ruth were playing today? And a lot of this you also have to then take into account, well, what about lifestyles and training? We know certain things are bad for you. We also know certain things can improve your performance. How do you take all this into account? Okay, so here are the key facts, the key parameters we're going to use. So RS observed is the observed runs scored. It's the average number of runs a team scores per game. RA is the observed average number of runs you allow. And gamma is some parameter, it's a constant for sport. So you can have a gamma for baseball, a gamma for basketball, a gamma for hockey. Anybody know which sport is probably going to be best for the sabermetricians to study? Baseball, hockey, basketball, football, soccer. You need to know a little bit about professional sports for this. Why baseball? Baseball has the most games. Baseball has 162 games. Hockey and basketball, I believe, is on the order of 80. Football is on the order of 16. So a factor of 2 and a factor of 10. The more observations you have, the more confidence and comfort you have in what you observe. You are not often allowed to gather more data as freely as you would like. It might be really convenient if I could give 7 of you COVID and see what happens. And just not have you guys wear masks, go back to your roommates and whatnot, or your pods. I'm not going to do that. But Google or Facebook, if they want to see how effective are different ads, different fonts, different placements, they have so many hits coming to websites, they can run these experiments very easily. And so always think about which data can you get, how confident are you about the stuff coming out. And so what Bill James observed numerically is that a team's winning percentage, number of wins divided by number of games, is extremely well approximated by runs scored to the gamma over runs scored to the gamma plus runs allowed to the gamma. And he was doing this a couple of decades ago. He took gamma to be 2. Best studies now say for modern day baseball, it's around maybe 1.8, give or take a little. Why do you think he called it the Pythagorean one-loss formula? Runs scored squared over runs scored squared plus runs allowed squared. Why would he call it Pythagorean? What do you think of when you hear Pythagorean?
theorem.
The Pythagorean theorem, a squared plus b squared is c squared. We have a sum of squares. And so we gave it the name Pythagorean. It's a good name. You want something that people are going to look up a little bit. So for example, in 2009, the Sox were 95 and 67, scored 872 runs, allowed 736 for a predicted record of 93.4. The Yankees were 103 and 59, but predicted to be 95 wins. One of the reasons we care about something like this is to try to get a sense of how good are teams actually and how much of the performance is luck. A lot of times this is then attributed to how good of a job does the manager do in terms of using the talent on the team wisely. All right, so here are three big examples. Extrapolation. So you can look halfway through the season and try to predict how a team might finish based on how they've started. And so a lot of times there's going to be some luck that's going to happen in games. I was watching one game where it was really good. The Yankees were about to lose to the Mets. There were 2 outs. The Yankees were down by a run. It was the bottom of the ninth. There were 2 outs. You're a couple of men on base, but it's a pop-up to the second baseman. All the second baseman has to do is just catch the ball. Full credit to the Yankees. They were running hard on contact because it's 2 outs. Second baseman dropped the ball. And 2 runs scored and the Yankees won. That should have been a game won by the Mets, but you are going to have things like that. By trying to get a sense of how good is the team, you can try to remove the effect of luck. And if you own a team, you can try to decide, are we in playoff contention? Is it worth trying to make a move and sign somebody at the trade deadline and maybe give up some of our prospects? Or do we say, oh my God, we're bad, but all of our metrics say we should be even worse than we are. This year is a loss. Let's conserve our farm system. Let's conserve our young prospects for next year. You can try to look and see if you are consistently overperforming or underperforming. And a lot of times that's used to attribute to the manager as to how well the resources are being used. One thing that's really nice about this formula, but it's less important in the 21st century than it was when it first came out, is it's easy to use. It's not a long, complicated thing like a quarterback ranking formula. I can just really give it to you. Run scored to a power over run scored to a power plus runs allowed to a power. It's simple. You can also see very quickly, well, what happens, is it better for me to score 10 more runs per year or to allow 10 fewer runs? You can try to get a sense of, do I want to work on my pitching or hitting? You have a nice closed form expression that gives you the power to make predictions. You don't have to resort to simulations. But because it's so simple, it's going to miss a couple of things. So a more complicated formula that a computer can use, there's a lot of advantages to that. But if a simple formula works and you can talk to people about it, there's power in that. And you can try to think, if you want to go to the State House and say, we need to change the metrics, what kind of pitch do you want to make? Years ago, I watched a congressman on C-SPAN talk about the exponential function and what's going to happen to the US deficit. And I was very thrilled to see math being discussed in the Capitol building. And I was not necessarily convinced how many people understood just how quickly things can accumulate. Know your audience. If a simple formula can have almost the same predictive power, it's not a bad thing to use. Or at least to use to explain things and say, and then we can tweak it a little bit to do a little bit better even. Okay, so I wanted to do a little basic probability because I know not everyone has done probability, or for some people who have done it, it may have been a few years, a few decades. So the goal is to model some observed scoring distribution. So for example, maybe this is how many is a histogram, and this will be how many times 0 runs are scored, 1 run, 2 runs, 3 runs, whatever. So a little bit more mathematical, we have some curve that's non-negative, and the area under it is 1. And that's going to be a probability distribution. So if you've taken a calculus class where you found areas under the curve, and they've never told you this is useful for probability, no court of mathematicians would convict you if you did something to your instruction. It is a crime to teach integration without saying probability. This is why we care so much about areas under curves. Only once in my life has someone come up to me and asked me for areas under curves unrelated to probability. And I was in Berkeley at the time, and you have a lot of strange things happening there. So most of the time, area is probability. So if I want to find what's the probability between 0.2 and 0.6, I just find the area under the curve from 0.2 to 0.6. We typically use capital letters to be random variables, and P is often the probability. Next concept is the mean or the average value. So we just integrate our density P times X. And if you have a discrete distribution rather than integrating, you can do sums. The variance is how spread out things are. So you look at X minus mu squared times the density. If all the mass is concentrated essentially at the mean, then the variance is very small. The larger the variance is, the more spread out things are. So if you look at one section, say, section 1, everybody gets a 50 out of 100. The mean is 50, and the variance is 0 because everybody has the same score. If you look at section 2, and half the kids are 100 and half the kids are 0, it's still the same average, but now it's got a lot more spread. And then the last is independence. Knowledge of one random variable gives no knowledge of another. Can somebody give me an example of dependence related to Mountain Day happening? Yes?
If Mountain Day isn't today, then it's other chance to be, so there's no chance to be today, so it's chance of the next two.
Right, so the chances of the next two are going to be going up significantly. Weather, given that it was raining, there is a much lower chance of having Mountain Day. It might be interesting to just surprise us, haha, you thought we wouldn't call Mountain Day during a tornado. But of course, that's probably not going to happen for good reasons. Do you think what happened in the baseball games last night has any impact on Mountain Day? So that would be an example of an independence. Anybody watch the old Charlie Brown baseball movies? Anybody? So here are the guidelines for modeling. They should capture the key features of the system, and they should be mathematically tractable. Any thoughts as to why I have a picture of a very sad Charlie Brown on the pitcher's mound here? So I want something that captures the key features and is mathematically tractable, solvable. What could be the problem? So what do you think happens as you capture more and more features of the system? Yes? Yeah, it's going to be harder and harder to solve it. So the more things you capture, the harder it's going to be. I was talking to somebody recently about, the planetary problems. If you want to figure out the orbit of the Earth, boy, it would be really nice if you just assumed that there's only the sun and the Earth. What do you think is the next most important heavenly body in terms of the orbit of the Earth? So Jupiter is one of two candidates. There's one other candidate. I would say Jupiter is one of the two candidates because Jupiter is extremely massive. The Moon. I would say those two would be the most important ones to look at next. Mercury, Venus, Mars, these are small planets. When you were looking at the orbit of Uranus, the planet Neptune was enough to noticeably change its orbit when the two of them were close to each other. But when they were far away, it was not really having an impact. So you want to capture as many features as you can and still have things solvable. Sometimes that's no longer possible. And then you resort to simulations. So in the paper we discussed in the last class, my colleague says, we had to do a huge number of simulations to see what was going on. When the Great Recession hit, I was teaching a senior seminar, and we actually did some numerical simulations to have a range of predictions of what would happen to the Williams portfolio. And rather than just saying, this is what it's going to be, here's a bunch of simulations, and we have a very high degree of confidence that it'll be somewhat in this range. So here's a possible model for baseball. And for those of you who don't really know what baseball is, you have two teams. You can only score when you're batting. Whoever scores the most runs wins. and you cannot have a tie. So some sports have a tie. We do not have enough time in this class to go into why it would be such a catastrophe if a baseball game ended in a tie. Just accept that it would be worse than the COVID pandemic if something like this happened, and the commissioner ruled that this will never happen again in baseball. And so we are able to prevent that horrible occurrence from ever happening again. So a game will not end in a tie. So here's a possible model. Assume runs scored and runs allowed are independent random variables, and they have some density functions. So we'll say F for runs scored and G for runs allowed. And if I want to calculate the probability a team wins, there's two different models I can do. I can do the sum version. So I assume I score I runs, and I allow J, and I sum over all I and J such that J is less than I. Or I could do the continuous integral version. I could integrate over all x and y, where y is at most x. If you want, you could do y is strictly less than x, but because a line or a curve has 0 area, I can do y is less than or equal to, not just equal. For baseball, which do you think is a better model? The discrete version, where you score integer numbers of runs, or the continuous version? Yes, the discrete version. As much as I would love the headline, Red Sox triumph over Yankees, pi to E. I'd love to see a score like that. Actually, after the season, I just love to see Red Sox win, but I'd love to see, numbers like that. We're never going to see that. However, we will use the continuous version and not the discrete version. And the reason is many of you have already taken 3 calculus classes. You've put in the time to learn integration. It turns out we can handle integrals a lot better than we can arbitrary sums. And so it's more convenient to look at the integral version and kind of smooth things out a little bit. So we're reduced to trying to calculate this, and we'll do the integral version. But before we do this calculation, let's look at the model again. I made some assumptions. Almost every model you have to make assumptions. The question is, are these assumptions reasonable? Do you think it's reasonable to assume runs scored and runs allowed are independent? Or do you think there could be a dependence between runs scored and runs allowed? Yes. Yeah, if you've scored a huge number of runs and you have a tremendous lead, you might put in worse pitches. Years ago, the Sox were leading 10-3 going into the bottom of the 9th, or going into the top of the 9th, I think it was a Fenway. So they brought Rumlinger in. Normally when you bring in a pitcher, you say what the pitcher's ERA is, how many runs they allow per 9 innings. They couldn't do this for Rumlinger because while he had pitched for the Red Sox and he had allowed runs, he had yet to record an out. So the denominator was 0, and they didn't actually have the graphic for the sign of infinity. So they just had 3 dashes for his ERA. You would not bring him in the season when it's a close game. Look at that, we're up by 7. He proceeded to allow, if memory serves, a grand slam. He actually was able to get the save. When you hear save, you think, they did something, they saved the game. Does anybody know what the definition of a save is in baseball?
Finishing a game where you still get the win from a pitcher where the run difference is 3 or fewer.
Almost. So what was said by Zoom is if you finish the game, if you're last pitcher and you win by 3 or fewer runs, you get the save. There is another way to get the save.
Or 3 full innings at the end.
Or 3 full innings or more, no matter how much the lead is. So years ago, the Texas Rangers were playing the Orioles, and after 6 innings, the Texas Rangers had 14 runs and the Orioles had 3. The Rangers brought in a relief pitcher for the final 3 innings. It's an 11-run lead. There's 9 outs to get. You could alternate home run out, and still win the game. Texas, however, continued to score. They scored an additional 16 runs. The final score was 30 for Texas, 3 for the Orioles, and the Orioles pitcher records a save. So Billy Beane in Moneyball, they talk about how he realized the save statistic was overvalued. And the on-base percentage, the ability to get on base, walking, was undervalued. And so he was able to make trades. Oh, you want my star reliever who has all of these saves? Oh, I hate to part with him, but I need a second baseman. Okay, you talked me into it. You can't keep doing this, but for a while, you can take advantage of these inefficiencies. If you're losing by a lot, you might also put in weaker pitchers. Earlier this season, maybe a week or so ago, the Yankees were playing the Red Sox, and the Red Sox were leading 9-1 going into, I think, the 8th inning. And the Yankees put in their right fielder. And they said, look, we've lost the game. We're not going to deplete any of our pitchers that we care about because, unlike the Red Sox, we actually have a chance to make the playoffs. And so we will save our resources for the next game. So there's a lot of reasons why you might have dependencies. There's one other major dependence between runs scored and runs allowed where they cannot be independent.
You can't tie. So if they tie, you're gonna
tie. So years ago, they still call it the Mother's Day miracle. The Sox are playing the Orioles. When you need something interesting, the Orioles seem to be involved in a lot of them. Going into the bottom of the 9th, the Sox were trailing 5-0. What do you know about the final score of the game? It won't be a tie, so it's at least not 5-5. And the Sox scored 6 runs in the bottom of the 9th, the final 1 or 2 coming on an error, for a walk-off win. So because they can't end in a tie, they can't be fully independent. And there's actually ways, for those of you who are taking statistics, where you can actually weaken this. And if you see like R by C contingency tables, there's ways to take this into account. It's also used in hospitals. Hopefully, if you go in for surgery, you don't come out worse than when you came in. So when you're looking at the possible outcomes, hopefully certain things will not be accessible states. There are the unfortunate times when they mix up what procedure they're supposed to do. And, terrible when that happens. But overall, you should at least be no worse than when you came in. And this is actually what got me connected with some major league franchises, is they noticed the non-standard analysis here of taking stuff like that into account. And so there's an appendix on this at the end of the slides, which I'll post, which talks about how you handle statistics like this. So we're reduced to calculating. So we talked a little bit about some of the issues with the model, and then you have the math issues. Can you actually do the calculation? And this is where the more experience you have, the better. So here is a possible model. Let's assume runs are just uniformly distributed. Do you think this model is baseball? No, so it's just not a good model. You could try a normal distribution. What's the problem with using a normal distribution to try to model runs scored? You cannot score negative runs. As bad as you are not going to score a negative number of runs. You could try an exponential distribution. And in something like this, the most common score is going to be 0. This is not a good model for baseball, but it might be a good model for a different sport. What sport might this be an okay model for? Soccer. Maybe 0 is not quite right to have as the most common. Maybe you want 1, but it seems a little bit more reasonable. So we're going to use what's called the 3-parameter Weibull distribution. So X is my variable, and I have parameters alpha, beta, gamma. Alpha scale, beta origin, gamma is shape. So what beta does is it just translates everything. You look at X minus beta. X is never by itself. It's always X minus beta. If you're looking at an NBA game, are you ever going to see an NBA game where they score 3 points at the end of the game? What do you think the minimum is going to be in a basketball game? Be conservative. 60. I might do 50 just to be extra safe, but you might say, well, look, I'm going to have some kind of distribution like this, but I'm going to shift the 0 point by 50 or 60. Alpha is just rescaling things. Think of it as converting from meters to feet. It's not going to really change how things look. It's just going to change your scale marks. Gamma is the real one that matters. As you change gamma, you're going to have things very different. So here's a plot of a couple of different values of gamma. When you have 1, 0, 1, so gamma is 1, you have a nice exponential distribution. And for the other values, gammas 2 and 4, you basically have these one bump distributions. The difference between the green and the cyan is I just have beta equal 2, so I'm just shifting everything over by 2 units. So these are nice distributions. They go up, they go down. And it turns out they model a lot of things. They model like survival times. It's wonderful how many things they look at. So, gamma less than 1 would be like high infant mortality. Gamma greater than 1, things survive for a long period of time. I'm just trying to give you a little bit of a sense of what's out there. I'm not going to go into too much detail on this. If you're taking this as 312, I recommend you look at this a little bit more closely. There's something called the gamma function, which generalizes the factorial. Gamma of n is n minus 1 factorial. And you can calculate the mean and the variance of a Weibull in terms of special values of the gamma function related to the parameters. There's a nice closed form expression. These integrals can be done. And the reason I was led to the Weibull was from some classes I had taken as an undergraduate in physics, where we were looking at things like the Maxwell-Boltzmann law and stuff like that, is I knew certain distributions, and I was experimenting which distributions will have integration that I can do. And so this is just going through the calculation of how you would find the mean. This is a snapshot of one of the websites. It might be MLB, I forget which one. And this is a little bit expanded. So if you look at any website, space is at a premium. Because we have to have ads, right? And the more stuff you have, the fewer ads you get. So they only want to put in stuff that truly matters. Team name, that's kind of important. How many wins and losses they have, that's important. Do you need the winning percentage if I give you the wins and the losses? No, it's nice to have. And then they have how many games behind are you? Again, I could calculate that, but it's nice to be able to just quickly look down and see. Then they'll tell you how they've done in the last 10 games, what kind of streak they're on, how they are in interleague play, their home record, their road record, and then XWL is their expected won-loss percentage. It's the Pythagorean prediction. And so you can see that they were predicting Boston to be 36 and 26, and they were 37 and 25. It's actually pretty close, at least for that one observation. I'm going to skip these slides. This is just another way of trying to model things. So the Pythagorean win-loss formula is if you assume runs scored and runs allowed are drawn from independent Weibulls, then when you go through and you do the calculation, you actually get run scored to the gamma over run scored to the gamma minus runs allowed to the gamma. There's a little technicality. Because baseball is discrete, we're not scoring continuously. I don't want to have my bins go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, because then all the action is happening at the boundary of the bins. Where do you think I want my bins to be centered at? So I don't want 0, 1, 2, 3, 4 to be at the edge of a bin. So which bin should include 0? Where should it start and end? Which bin should include 1? Yeah, so I would go from maybe 1/2 to 3/2, and now 1 is right in the middle. 3/2 to 5/2, 2 is right in the middle. So it turns out we're going to take beta to be either a half or negative half, just so that all the scoring is now at the right middle of the bin. And so if you go through and you try to calculate, what are the values of these parameters, you can relate these parameters very nicely to the average number of runs scored and runs allowed. And this is just going through and using those formulas. And now we just want to calculate what is the probability that x is greater than y. So if you've done multi-variable calculus, this is now a double integral that's worth doing. Again, I'm not going to go through the details of this. I encourage you to just go through and see it afterwards. If you are a physics person, there's a lot of really nice action happening here, which if you've seen resistors in series and parallel, it might remind you of something like that in terms of effective mass and some gravitational problems. There's some really good ways of looking at the algebra. But the point is, we can actually do these integrals. And it's not a coincidence. I deliberately chose the Weibull because the Weibull not only captures a lot of shapes, but it leads to integration that can be done. I don't think baseball is governed by Weibulls, but I think it's not a bad approximation. One of my thesis students actually looked at, well, what would happen if we had combinations of Weibulls? Would that give us a better sense of what's going on. All right, so when the dust settles, you end up calculating very nicely the probability that x is greater than y. So let's choose a year at random. Let's choose 2004. Here is the data for runs scored and runs allowed for the Red Sox. And I'm plotting the best fit Weibull. Do you think this does a good job, yes or no?
Yes.
Yes. Do you think it's a perfect job? No. And I would be shocked if it was perfect. But it's not horrible. This is, of course, a clarion call that we need to learn statistics so we can do something better than visually it looks good. We want to be able to quantify how good is it. And so what we can do is we can break up scoring into different bins. And what we can do is we can look at what is the best fit Weibull. We want to minimize the error between how many times we should score 3 runs or be in the 3-run bin, and how many times it actually happened. And so the smaller the difference, the better the fit. The larger the difference, the worse the fit. And so we just look at summing the squares, and we square the errors so that you can't have a negative error canceling with a positive error. You could do absolute values as well, but if you square, calculus is available. And so when we do this, we find the best fit Weibulls. So here's the Red Sox. Here's the Yankees. Here's the Baltimore Orioles. Something might be going on there. Tampa Bay Devil Rays, they were the Devil Rays back then. They may have had a bad record, but they had a really nice Weibull decay in their run score. And what about the Toronto Blue Jays? Good fit or bad fit? Or at least as good as or worse than the others? Worse. But you have to remember, the Toronto Blue Jays are a Canadian team. No, okay, metric has nothing to do with this. It would actually be suspicious if all of the data were good. And the reason is some advanced theory. So if you were to flip a fair coin 1,000,000 times, you'd be exhausted. But you would also expect about 500,000 hits. Would you be surprised if you had 503,216 hits? What if you had 528,000? What if you had 580,000? At what point does it get surprising? If you have 800,000 heads, I think you'd be surprised. About 95% of the time, you'll be within 1,000 of 500,000. That for a lot of problems, the fluctuations are of the size square root of the number of things you do. So the square root of 1,000,000 is 1,000. So when I said 503,000, that would be very surprising to be that much. And so if you consider n independent experiments, so n students in class each decide to flip 1,000,000 coins and record, are you outside that range? If 5 people do it, there's a 22.62% chance that at least one of you will be outside that range. If 14 of you do it, which was how many teams were in the American League back then, there'd be a 51% chance that at least one of you would be outside that range. If 50 of you do it, there's a 92% chance that at least one of you will be outside that range. Unlikely events should happen if you have enough things going on. A terrific example of this is, I guess we're going to now have the students tested twice a week. I'm expecting some false positives. Just because of so many tests happening. And this is going to have issues for the local school district. So if all of the data is really good, I get a little suspicious. Because there should be some unlikely events happening when you have so many things happening. And so I'm not going to go into details to what exactly is a chi-squared test. If you've seen statistics, that's wonderful. All I want you to know right now is the larger the value of chi-squared, the more likely it is that it's not a good fit. And so the threshold for looking at, say, runs scored and runs allowed being well approximated by the Weibulls, it should be 31.41 or lower 95% of the time. And if you look at this, there's only one team that really jumps out at you, and it's the Toronto Blue Jays at 41.18, which actually fits visually what we were seeing. there's something called the Bonferroni adjustment, which you haven't seen. If you haven't seen your statistics class, it's really worth looking at. It says, look, if you're doing so many tests, because you're doing so many tests, it's likely for at least one of them to come back as significantly different when really nothing is happening. And so you get to adjust the numbers and you get to inflate the numbers a little bit. And so rather than 31.4, it inflates to 41.14, which is now essentially what the Blue Jays are at 41.18. And so this is all very consistent that this is doing a good job modeling. So I'm not going to talk about details. I just have a slide here that there are ways to handle what's called structural zeros, places that are inaccessible. When we're looking at, are runs scored and runs allowed independent, the answer is no, because they can't be equal. But effectively, they do behave as if they were independent. And yes, the comments you had that if you're scoring a lot, you might put in different people, give somebody else a chance to hit, put in a weaker pitcher. There are dependencies, but these seem to average out over 162 games. So just quickly summarizing, looking at 2004 year, you can look at the observed wins, the predicted wins, the observed winning percentage, predicted winning percentage, the game differential, and the best fit value of gamma. So I'm getting gamma by doing each team one by one by one by one. And we get gamma, its mean is 1.74, the median 1.76. This is not too far off from the observed best of 1.82. On average, typically you're about 4 games off. Some teams a bit more, some teams a bit less. The Yankees were plus 13. And this seems to be indication that Joe Torre's years with the Yankees, he was consistently doing better than what was predicted. So it looks like the Weibulls are actually doing a good job. Even though I don't believe it's the truth, it actually captures enough of what's going on. The runs scored and runs allowed do seem to be statistically independent. We now get the Pythagorean formula as a nice consequence of our model, and our results are pretty close to what's being observed. Just a little bit for future work, and some of this has been done, is you can now try to incorporate higher order effects or lower order terms. One thing you might do is, what if you're up by 10 runs with 1 inning to go? You might say, we now declare the game has been won by the home team, and all runs scored from this part onward do not matter. Because you're putting in garbage pitchers, or the other team might even be putting in garbage hitters to give them some practice. And so you might try to adjust your numbers and take into account. So this is the wonderful thing about having thesis students. I had a thesis student who did this, and what he found is there was really no significant improvement in predictive power from incorporating effects like this. Which is great, because it's a lot more work to do this. You would actually have to look at the box score of each game and say, at what point are you making the ruling that the game is over? There was a little controversy earlier this year because somebody for the San Diego Padres, I'm blanking on his name, the Padres were up by, I think, 7 runs. It was a 3-0 pitch to him, and he swung, and it was a meatball, it was a marshmallow right down the middle, and he hit a grand slam. And people were yelling at him, why are you swinging on a 3-0 count? Well, until the other team forfeits, the game is not over. And people have come back and overcome deficits like this. But most of the time they don't. And so you might actually say, look, we don't really want this to come into play, but it's a lot more work to go and collect all these statistics. If you don't have to, if the simpler model will do as good of a job, that's great. And you can sometimes do some tests and see how much more predictive power do I get if I actually go through all this effort. And you want to really focus on which statistics matter the most. So the last thing I want to do, and then we'll call it a day, is seize opportunities. You never know where they will lead you. And this is probably one of my favorite slides. This is Oliver Smoot. You cannot make this up. He became chairman of the American National Standards Institute and president of the International Organization for Standardization. I'm just trying to imagine some of his job interviews. Well, I don't want to brag about my background, but I am a unit of measurement. And so, he could have been upset about what was going on, or you can roll with the punches. And you can have a nice, compelling human story, a way to make a connection with people. Years ago, I taught a winter study on cryptography, and I encrypted the title. And Williams College was, you want on students' transcripts? Absolutely. It will be a conversational style. And several students told me when they were being interviewed, he was like, I gotta ask, what is this on your transcript? And now all of a sudden it's a conversation on the subject that they're interested in. All right, so again, a lot of good stuff today on how to do mathematical modeling. And then for those of you who are looking at stuff like this, talk to me and we'll discuss what do we think is going to be truly essential in what you're doing. All right, have a great weekend. We put up some references. I'll just go through this, so if anybody ever wants to, they can just hit pause, and it will now at least be displayed.